Hello, Zig Stockholm. My name is Isaac Yamamoto, and today I'll be talking about Zig FFI for great justice. This talk will be using Zig to do FFI in the Elixir programming language. All right, so why would you ever do something like this? Well, first of all, let's talk about the advantages of running a programming language like Elixir. So Elixir runs on a VM. The VM that it runs on is the same VM for the Erlang language, and it's called BEAM. Don't ask why it's called BEAM. BEAM is a high-level programming language VM. There are more than one languages that target this VM that is really focused on supporting failure domain isolation, concurrency with no shared memory, and a per-thread garbage collector. It has very battle-tested network primitives and very battle-tested distribution support. Classically, this virtual machine was designed to be the control plane for telephone switches, but more recently it's found a lot of use as the control plane for switches, network switches, as well as for websites, because it turns out that that domain of execution is very similar to what you would expect for telephone switches. But by no means are these the only uses that it's useful for. We're seeing a lot of data science and machine learning applications emerging, especially given the strengths of Elixir. Okay, but despite all these great features in language, sometimes you need low-level like OS primitives. For example, if you want to access a network socket, at some point that's not doable using the built-in programming language, although there is a socket module that itself is built in an FFI. A lot of the internal parts are being transferred from native C code in the virtual machine to FFI built primitives. Sometimes you need speed. So the Erlang VM uses box types. And unfortunately, box types are very slow for math. So on the right-hand side here, I have the stats report from the infamous Dave's Garage performance drag race, where you had to try and write the fastest sieve of Eratosthenes algorithm. And you can see here that Zig has an extremely fast implementation with which was the fastest, so we'll make that a reference of 1, and Elixir was 1,300 times slower. In many cases, when you're doing network type coordination, the network is really your slow step, and having a solid set of a solid VM that's designed for failure domain segregation and designed for concurrent operation, and also gives you a whole bunch of really nice tooling around it. This sort of CPU performance doesn't matter, but there are increasingly more and more use cases where you want some sort of hybrid of good I/O throughput and good CPU performance, and so this is a case where you would consider doing FFI. Before we go on, I need to tell you a few things about Elixir. We'll try and keep it limited to the minimum that you might need to know. So in Elixir and the Beam, all code must be contained inside a module. So these are conceptually just namespaces, but they're also code units. So each module gets compiled to a .beam file. If you're used to something like the Java virtual machine, you can think of this as like a jar. I believe Python also does compile things into PyC files, which are compiled Python bytecode. Erlang's code itself, which is sort of the progenitor language, looks a lot like Prolog. Elixir tends to look more like Ruby, so it's more friendly to programmers familiar with like Algol style. So C, Zig, Pascal. So you'll so hopefully we'll be able to read the Elixir code without too much of difficulty. And the last thing to know is that the Erlang VM is a dynamic VM. So any given term can carry any type of value. On the other hand, it's a very simple type system. There are only a handful of actual types. So integer are type, floats are type, linked lists are type. There are binaries, which are immutable slices of U8. We have hash maps. We have atoms, which are intern strings. And by the way, that for the hash map, that first, the keys in this case that I've shown there are atoms, but they could be any other term. They could even be another hash map. We have tuples, which have the corresponding syntax, and then there are a few like VM-specific things called ref, PID, and port, which I won't get into too much detail. Although PID does refer to the executing green thread. So how would you do FFI in the Beam with C? So I'm going to show you some C code, and then we're also going to show you the integration code that's used to integrate this C into your module. And what I want you to do when you're looking at the C code is to take note of all of the places where you can see potential difficulties. So I've tried to create as accurate as possible an implementation of the following very, very basic function. And so let's take a quick look. So this is the FFI for a simple function that will take two values that are both integers and add them together. So actually, let me move myself to the bottom so we can see this correctly. Okay, so let's go ahead and run this. And the wrapping module for this looks something like this. I'm going to basically overload this function called the sum function. So you can see here I've written a sum function which takes a left value and a right value, and it's going to print out computing from the VM and then return the value of the two. So let's run this. And when we compute from the VM, we get the value that we expect. If I say pass something dumb, which would be an atom, so you can't add atoms, we're going to get an arithmetic error, bad argument, and arithmetic expression with a very nice error statement. Now what we're going to do is we're going to compile the C code here, and let's make an alteration so that we can see that we are actually creating something new. So we're going to say now computing from the NIF. And then what we're going to do is we're going to run c.compile. So normally you wouldn't have to write this. I've just put this here to show you that we can run zigcc from the command line and run something. A normal module you would probably have to write some sort of make file or something that does all these steps for you as part of your execution. Now you see that we've successfully compiled. This is the error value from the execution of zigcc. So that's a 0, so that's good. And then what we want to do is we're going to init, which will overwrite any sort of functions that are created by this NIF, and I'll show you how that's done in a moment. And what we'll see is that the sum function gets changed and turned into the one that we're executing from the C file. So let's go ahead and do that. C.init. And then now if we run c.sum to 3, we're going to see now computing from the NIF, and the result is 5. If we do something weird, like 2 and then foo, we're going to get something a little bit different. So let's take a look at this code. So a few things. In order to create a NIF, which is the vocabulary for FFIs, we had to call this C macro called earlnif init, which expands to this basically. And what it does is it sets up a catalog of all the functions based off of this static list. And this tells me I'm going to take the toArity function, sum, so two arguments, and overload that in the module with the function sum. So that's a function pointer. And then here's the function pointer. I have to pass this environment thing, which is a pointer to the heap of the executing environment, for better or worse is the best way to describe it. The number of arguments that you expect, and then this C array, which, as you know, if you're a Zig practitioner, can be a little bit of a squirrely item, but at least we have a length and an array pointer here. We're going to go ahead and do this printf. Then we have to manually unwrap the int values using this enif get int. We're going to pull that, and then we're going to put that into this left pointer. If it doesn't work, we're going to create this left argument not integer atom and turn that into an exception. Okay, so you can see that this is like not very easy. And then when we're all done, we do the left plus right bit, and then we rebox that into an integer term and send it back to the calling frame. All right, this is like a lot of hassle. And it doesn't even produce a pretty error, the pretty error that we were hoping, a pretty error that looks like the nice error that we're hoping for. It's possible to do this, but this would be even more code to get this to look right. So I think like it goes to really highlight just how annoying and nitpicky and finicky doing all this is. Everything from getting all the bits and pieces in C correct to like mounting it correctly into the module like so, and then setting up a make file or whatnot to make sure that all that gets compiled when you're building your program release to be deployed. Okay, so now that we've taken a look at that, I'm going to show off Ziggler. So let's look at the equivalent Ziggler code to the C. And Ziggler, which is the library that lets you do this FFI, makes a couple of choices. The first thing is that it embeds the primary Zig source code in Elixir code. You can definitely like import other Zig files, so you're not confined to being in the same module. But the reason why I chose to do this is because it just gives one less layer of indirection if you're doing code review. And the other thing that it does is it automatically fills out all that boilerplate for connecting the Zig code to the Elixir code. So let's take a look at the equivalent function here. So here is the equivalent Zig to the previous function. So here we have this, we just use Zig, and this brings in all the Elixir parts of the compile time machinery to get this done. And then we just literally write our Zig code in this sigil Z string. I actually have a VS Code formatter, which will make this look pretty and highlight it as well. And as you can see, we eliminated almost all the ceremony. All we had to do is mark our function as public, and then declare all of the types that we care about. And then we go ahead and just perform the operation and return the result. So let's go ahead and run this. Oh, while we're at it, let's change this one as well. Now computing from Ziggler. So Zig equivalent dot sum, and then let's sum 2 and 3. Oops, we should recompile it. There we go. You can see Zig compilation occurring. And then when we run this, we get now computing from Ziggler. And if we do something dumb, like pass something that isn't working, we get a nice argument error that says we expected an integer for the second parameter, for the second argument, for the Zig type I32, and instead we got foo. So yeah, and all that was handled automatically by Ziggler for you. You didn't have to do any of the fiddly bits. Okay, so the next thing I'm going to do is I'm going to walk through a slightly more advanced example to really show you how all this marshalling works. So in this advanced example, what we're going to do is we're going to execute this run program, which takes this payload of my struct. So here I've got this type my struct, which is an array, which takes an array of integers and performs some operation. And that operation, we're going to use some enum of add and mul. And if that gets passed, if it's add, we're just going to add up the entire array. And if it's mul, we're going to add up the entire, or we're going to multiply together the entire array. Okay, so let's look and see what happens when we run this. Zig advanced dot run. And so, what would you expect structs to do? Maybe a hash map. And, oops. There we go. And now we see that we expected a map or keyword for mystruct, but the mystruct requires the field array, which is missing. Well, let's add an array in. 2, 4, 6. And now it says mystruct requires the field operation, which is missing. All right. But we need to get some sort of enum in there. Well, what we can do is this enum literal is known to the Zig compiler, and what will happen is that it will be serialized as an intern string. So we can just do add, and here we get 2 plus 4 plus 6, which is 12. If we did mul instead, we would get the expected multiplication result. I want to show you a couple more things. What happens if I, say, forgot a semicolon? Well, the nice thing is that we get this Zig with this error, lib Zig advanced EX19, and it points to exactly where that error occurred. And moreover, one more thing is, note that we had a doc string here, so we can run help. Oops, got to recompile it. And we can see here that not only do we have a type specification that shows that it's looking for an array of int32s. It can also, by the way, take a binary of int32s and turn that into the slice. And it tells you that the operation is expected to be either the atom add or the atom mul. And the documentation here that we have performs either addition or multiplication on an array of integers is brought into the Elixir documentation. So let's talk about how this happens and how this works in a more step-by-step fashion. Well, the first thing I have to do is I have to do something I call file assembly. So what this does is it goes through the module and finds all the sigil Z sections and assembles them into a single file placed in the Elixir directory. So let's take a look at that. So in this case, Zig Advanced got turned into this elixir.zigadvanced.zig. And you can see that this file is basically a copy-pasted version of this file, with the exception that it's got like a little bit of a warning, and it's got these headers that tell you where it came from. And that is part of how this code winds up being able to map back those errors to where they occurred. Okay. The next thing that we do is that I do something called a semantic analysis pass. So bundled with a Ziggler library is an executable called sema.zig, which is a special file that performs semantic analysis at Zig compile time on the program and emits a JSON corresponding to the types and functions present in the file. So this is the primary source of truth that Ziggler will then use to figure out how it needs to generate the file. So in order to really quickly show you, I'm going to do dump schema true, and then we can do a recompile. And here in yellow, you'll see the JSON file that the JSON content, which is used to describe exactly what is in there. So we have a list of declarations, a list of functions, a list of types, and then they all carry all the payload of everything that you might need to successfully build this FFI interface. One cool thing is that comtime Zig means that the resulting artifact is a linear program with no control flow. So the entire purpose is just to emit the flow. It's very fast. The third thing that happens is that we do a parser pass. So Ziggler then runs a custom parser based on Zig's grammar.y file that directly parses Zig code. So this has several purposes, one of which is to assemble the manifest of where each of those code segments comes from. And it's also necessary to produce errors on a lot of weird corner cases. So if I, for example, use a non-pub type in the function header, then this is the only way for me to extract that information and give you hints as to what it should do. And it's also used to turn doc comments into Elixir doc strings, which is what I showed you before. Finally, there's a code gen and compilation step. So Ziggler will build the .so file, but before that, it generates a shim file that contains module hooks. So the onload function that you saw in the C, the static array that is all of the functions that were used. It exports a load function, and it also generates all the code that marshals your data types in and out of beam.term. So let me quickly show you that file. Oops. Zig advanced. So here you can see something that is analogous to that C static function that gets created. We see this nif init function, and then we see the manifest of all the functions that were created. And then here is a marshaled function which shows you which has all of sort of the mechanical parts that are used to go to set up allocators and then to convert the output type here, and then also build the payload that then gets called into the function. So all of these things make that whole process are automated, and in some cases use Zig generics. So we know that those will always be error-free, and you don't have to deal with any of the muckety-muck of putting things together and converting them from the box types in the Erlang VM over to the unboxed types that you have in Zig. Okay. So let's talk about the power of Zig and why Zig makes this awesome. So the first thing that I'm going to show you are make and get functions. And I've been talking a lot about boxing and unboxing between statically typed Zig and dynamically typed Elixir. And I'm just going to show you a quick example of how that looks under the hood. So this is an example of make and get. And what this is effectively is an unboxed version of what I had before. And we're just going to go ahead and run this. So make get.sum, and then we're going to do 1 and 2, and oops, got to spell that correctly. And then you can see that it produced the result 3. And in order to unbox variables, all we do is we call this special beam.get function with the type that we would like to unbox into. We give the environment of the execution context and then the term. There are some extra parameters that you can put in here that are needed for certain types of terms, or optional in most cases. And we do the same thing on the right. And then when we're ready to convert it into a boxed term, we pass the environment, any sort of value here, and then the result. And the cool thing here is that let's say we wanted to change the type of this to be like a tuple, and then we wanted it to be an OK tuple. Well, we can pass like the anonymous. We can pass the anonymous enum here, or sorry, the enum literal here, and an anonymous tuple struct. And then if we recompile this, it will figure out how the sort of data type that we expect, and it will wrap that into it'll convert that based off of what it looks like in Zig into something very sane in Erlang. So if we do that, now we can see we get the atom OK with the payload 3 in this tuple. And it turns out that there's a very nice mapping between structs and maps, and tuples and enum literals and atoms that I'm able to take advantage of. And because beam.make has Zig comp time powers, it can look at what I'm trying to return and figure out how to convert that into the appropriate beam types. Resources. So one thing that you can do is you can create data that are tied to the Beam GC with callback functions that are registered to the GC. And normally this is a very, very fiddly process. I won't go into details, but it is incredibly easy to do using Ziggler. So let me quickly show you that. So in this case, what we do is we create a special resource type. We use this generic function beam.resource, which takes the type of thing that you're trying to build a resource. You have to pass the root in for reasons I don't want to get into. And then just here, you can create a callbacks option. You can create an optional callbacks type, which will include in this case the destructure function. So when this value gets destroyed by the garbage collector, this code will get executed in C land, or CABI land. Also, you have to declare the list of all the resources that you use in this module here. In this case, I'm just going to have an empty payload or a relatively empty payload that's just going to bear U8. And to show you some of the code that we're going to embed this in, what I'm going to do is I'm just going to spawn, which creates a new green thread in the Erlang VM, and it's going to call this run forever, which is a tail call recursive function. And this is how you do execution flow in green threads in Erlang. You wrap them in a sort of an enclosed tail call optimized function. So on the first pass, we're just going to get a default value of nil, which will create the new resource, and it'll just sort of a tail call around that resource, which keeps getting passed back to itself. All right, so let's do resource.launch. So what this has done is it is returned the PID, the process ID or green thread ID that is created by the spawn operation. And as you can see, we still haven't seen this cleaned up. And remember earlier in the talk, I mentioned that the GC is tied on a per process or per green thread basis. And so if I want to exit the green thread, I'm going to do process.exit. We're going to take the previous value, which is the special keyword v, and then we're just going to kill it. So we're going to exit. This is like kill -9 if you're used to shell script. And you can see that wound up jumping back into this callback. It cleaned up, and then it passed the value that the resource was created with. So it was able to see inside of that resource as part of the resource destruction callback. Second thing that's very useful about Zig is that it is allocator agnostic. So one thing you should know is that the Beam comes with its own allocator that is extremely useful for placing data close to where it needs and improving the performance of code in the Beam. If you use malloc, then VM is both cannot place that where it thinks it should be, and it's also not aware of how much memory its NIFs are using. So I will show you that using the Beam allocator allows you to tie that in correctly. So here's an allocator module, allocator demo module, and all we're going to do is we're just going to create this leak function that's just going to allocate one meg of memory, and then just leak it. We're not going to do anything with it. We're going to lose the reference. It's all gone. And then this memory function is just a convenience function to show you how much memory the VM is currently using. So let's do this. And you can see there's about 5.7 million bytes. And then let's go ahead and run it. So we cause a leak, and now we have about 6.5-ish. Yep. So that shows you that the allocation is able to be tracked by the virtual machine. If you use beam.allocator, if you use malloc, that's not going to happen. It won't know that it's going on because it's operating at a level below what the virtual machine is able to see. So here's another benefit to Zig. There are several different execution modes that you can run your C ABI code in. And so there are a few restrictions. For example, all the code that I've shown you so far has been run in what's called immediate mode. This must complete in 1 millisecond. However, so if you don't do that, the scheduler can get out of whack and bad things can happen, nasal demons and so forth. There's a dirty mode, which can be dirty CPU or dirty I/O. These are run in special threads that the VM provides, and they're limited scheduling. So if one dirty FFI function is scheduled, then it blocks any subsequent calls that require that scheduler get blocked. So you can saturate your ability to execute those functions. There is threaded mode, which has no limit, but it has the overhead of having to spawn a special OS thread. And there's yielding mode, which creates an event. In the case of Ziggler, it will for you create an event loop shim that connects Zig async with the Beam scheduler. This is the probably the best mode that you can run in if you could. But note that because of the Zig's version 0.10 and 0.11 deficiencies, this is not supported. So it'll come back. The yielding will come back. But because Zig has uncolored async, it's very easy to write a single function and literally put in different entry points that point to the exact same function, and run each of those with almost no hassle. You don't have to rewrite your code to handle being async or not, and all the behaviors should be more or less the same. And the last part of Zig is easy C. It's really cool that Zig understands C. And because Zig understands C and that follows through to the semantic analysis, we can use this to interop with C libraries in an especially convenient fashion. So what I've done here is I've whipped up a quick module that imports one function from BLAS. So BLAS, if you don't know, is basic linear algebra subsystems. And then there's this function DAXPY, which is operates on double floating point, double precision floating point numbers, and it's the AX plus Y linear algebra routine. So what that means is it takes a scalar and two vectors, x and y, adds them together, and then returns the vector that results. What's cool about this function is that DAX plus y has an in-out parameter. And so the fourth argument, so this is the length, how many items are in your vectors. This is your a, which is your scalar that you're going to add in. This is x. This is the stride for x, and this is your y, and then this is your stride for y. So how many items will you skip over, or how many indices apart are your values? And what's interesting is that the result is placed back into the fourth parameter. And so to annotate that, I here say, as an option, I provide, hey, when you run the DAXPY function, your return is going to come from the fourth argument, and the length of that array is going to come from argument 0. So that's going to be your length. So let's go ahead and run this. And you can see that the result it gave was 7, 11, 15. That is AX, so that's 3 times 1, which is 4 plus, which is 3 times 1, which is 3, plus 4 is 7. 3 times 2 is 6, plus 5 is 11, and 3 times 3 is 9, plus 6 is 15. So this is the DAXPY, and note that the result came from what was put back into this in-out parameter in the original C. Okay, so that's what I have to show. In summary, Zig makes building FFI logic extremely easy. There are lots of really nice compile time features both on the Elixir side and the Zig side. They really work together to eliminate error-prone parts of writing FFI. And I spent a lot of effort to make import beam enable Zig to do things in the beam idiomatically. And this is basically an advantage that no other programming language that you can do FFI with has whatsoever. I see in the future this could be even potentially better, where, for example, we can do something like bind malloc to zlibc, statically compile, or bind malloc, the zlibc malloc to beam allocator, and then compile other programs, external programs, for example, BLAS, which might need to allocate memory here and there, and then use those in a way that memory can be tracked by the beam. And this provides good merging of Elixir and beam features with Zig. So hopefully, if any of you have adventures in building FFI for other programming languages, you can take some inspiration from this to make your interface with Zig be as idiomatic as possible to the ecosystem that you're building your FFIs for. Okay, hope you found that to be interesting, and thank you for your time.